Installing multiple primary cables in the same conduit, even if the conduit appears sufficiently large, is generally not advised. This caution arises from several potential issues. Firstly, proximity effects. When multiple conductors carrying high voltage current are placed in close proximity, they create magnetic fields that interact. This interaction can lead to increased inductive losses and subsequent heating of the cables. Secondly, insulation deterioration. The heat and magnetic fields resulting from proximity effects can damage the cable insulation over time. This damage can ultimately result in cable failures and system downtime. In this specific case with 25 kV primary cables, while not ideal, circumstances may necessitate pulling multiple primary cables in the same conduit due to space limitations or other constraints. If that is the case, the fact that the primary voltage is 22 kV below the 25 kV rating of the cables implies the cable should handle the current at that voltage without necessarily overheating, assuming all other factors are within acceptable limits. However, adhering to several critical conditions is paramount. Firstly, ampacity. It is essential to verify the conduit size and cable ampacities. This verification ensures that the cables will not be overloaded when operating under normal conditions. Secondly, conduit fill. The conduit should not be filled beyond 40% of its capacity with cables. This limit allows for adequate heat dissipation, preventing the cables from overheating. Thirdly, conduit ventilation. Adequate ventilation of the conduit system is crucial to prevent heat buildup. The system should facilitate airflow to dissipate any heat generated by the cables. Additional considerations include cable splicing. When splicing multiple cables within the same conduit, use heat shrink splices specifically rated for high voltage applications. These splices provide reliable insulation and prevent electrical failures. Grounding. The conduit and all metal fittings must be properly grounded. Proper grounding prevents electrical shock hazards and potential damage to the cables due to fault currents. Regular inspection. Regularly inspect the conduit and cables for any signs of heating, damage, or insulation deterioration. Early detection of problems can prevent major failures and ensure the long-term reliability of the system. In conclusion, while not generally recommended, pulling multiple 25 kV primary cables in the same 4-inch conduit may be acceptable under specific conditions. However, meticulous attention to ampacity, conduit fill, ventilation, and other critical factors is absolutely essential. Careful consideration and consistent maintenance are vital to prevent overheating and potential cable failures, ensuring the safe and reliable operation of the electrical system. To elaborate further on the importance of ampacity, it's crucial to understand how it relates to the National Electrical Code, NEC. The NEC provides tables, such as Table 310.15b16, which list the allowable ampacities of insulated conductors based on factors such as conductor material, insulation type, and ambient temperature. These tables are essential for determining the maximum current a conductor can carry continuously without exceeding its temperature rating. When installing multiple cables in a conduit, the NEC requires adjustments to these ampacity values due to the increased heat generated by multiple conductors in close proximity. These adjustments are outlined in NEC section 310.15c. The adjustment factors account for the reduced heat dissipation capability of the conduit system when multiple conductors are present. For example, if you have 4 to 6 current-carrying conductors in a conduit, the allowable ampacity of each conductor must be reduced to 80% of the value listed in Table 310.15b16. This directly ensures that the conductors do not overheat and damage the insulation. It's important to note that the NEC also provides exceptions to these dirty requirements under certain conditions. For instance, if the conductors are installed in a raceway with adequate ventilation, the dirtying factors may be reduced or eliminated. However, it's crucial to consult the NEC and local electrical codes to determine the specific requirements for your installation. Regarding conduit fill, exceeding the maximum allowable fill percentage can significantly impede heat dissipation and increase the risk of overheating. The NEC specifies the maximum allowable conduit fill based on the type of conduit and the number and size of the conductors. These requirements are outlined in Chapter 9, Table 1 of the NEC. For example, the maximum allowable fill for a conduit containing 3 or more conductors is typically 40%. This means that the total cross-sectional area of the conductors, including insulation, must not exceed 40% of the internal cross-sectional area of the conduit. Exceeding this limit can restrict airflow and prevent heat from escaping, leading to elevated temperatures and potential cable damage. To ensure compliance with conduit fill requirements, it's essential to carefully calculate the cross-sectional area of each conductor and the internal area of the conduit. Use appropriate tables and formulas provided in the NEC or other electrical handbooks. In addition to ampacity and conduit fill, proper ventilation is crucial for maintaining safe operating temperatures. A well-ventilated conduit system allows heat to dissipate effectively, preventing the buildup of excessive temperatures. The NEC doesn't provide specific requirements for conduit ventilation, but it's essential to consider the surrounding environment and ensure that the conduit system is not installed in a location where it will be exposed to excessive heat or restricted airflow. For example, avoid installing conduits in direct sunlight or in enclosed spaces with poor ventilation. If necessary, provide additional ventilation by installing vents or louvers in the conduit system. These vents allow air to circulate freely, dissipating heat and preventing temperature buildup. Furthermore, proper cable splicing is critical for ensuring reliable and safe operation. When splicing high-voltage cables, it's essential to use splicing methods and materials that are specifically designed for high-voltage applications. Heat-shrink splices are commonly used for high-voltage cables because they provide excellent insulation and mechanical protection. These splices are made from a special type of heat-shrink tubing that shrinks tightly around the cable, creating a watertight and airtight seal. When installing heat-shrink splices, follow the manufacturer's instructions carefully. Ensure that the cable insulation is properly prepared and that the splice is installed using the correct tools and techniques. Improperly installed splices can lead to electrical failures and potential safety hazards. Grounding is another essential aspect of high-voltage cable installation. Proper grounding ensures that the conduit system and all metal fittings are electrically connected to earth, providing a lower impedance path for fault currents to flow back to the source. This helps to protect personnel from electrical shock hazards and prevent damage to equipment. The NEC specifies the requirements for grounding electrical systems in Article 250. According to the NEC, all metal conduits and enclosures must be grounded to a grounding electrode system. This system typically consists of a ground rod, ground plate, or other approved grounding electrode. The grounding conductor must be sized appropriately to handle the maximum fault current that could occur in the system. It's essential to ensure that all grounding connections are clean, tight, and corrosion resistant. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness. Finally, regular inspection and maintenance are essential for ensuring the long-term reliability and safety of high-voltage cable installations. Periodic inspections should be conducted to check for signs of damage, overheating, or insulation deterioration. Look for cracks, discoloration, or swelling of the cable insulation. Also, check for loose connections, corrosion, or other signs of wear and tear. If any problems are detected, take corrective action immediately. This may involve repairing or replacing damaged cables, tightening loose connections, or improving ventilation. Regular maintenance can help to prevent major failures and extend the lifespan of the cable installation. In addition to visual inspections, consider performing electrical tests to assess the condition of the cables. Insulation resistance tests, also known as Megger tests, can be used to measure the resistance of the cable insulation. A low insulation resistance reading indicates that the insulation is deteriorating and may need to be replaced. High potential tests, also known as HIPAT tests, can be used to verify the integrity of the cable insulation. These tests involve applying a high voltage to the cable and measuring the leakage current. Excessive leakage current indicates that the insulation is weak and may be prone to failure. By following these guidelines and adhering to the requirements of the NEC and other applicable standards, you can ensure the safe and reliable installation of high-voltage cables and conduits. Remember that working with high-voltage electricity is inherently dangerous, and it's essential to take all necessary precautions to protect yourself and others. Always to energize the circuit before working on any electrical equipment, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you're not comfortable working with high voltage electricity, it's best to hire a qualified electrician to perform the work. In addition to the points already covered, let's delve deeper into specific considerations for ensuring the long-term integrity of high-voltage cable installations within conduits, focusing on environmental factors, mechanical protection, and advanced monitoring techniques. Environmental factors play a significant role in the lifespan and performance of high-voltage cables. Moisture, temperature variations, and chemical exposure can all contribute to insulation degradation and premature failure. When installing cables in underground conduits, it's crucial to ensure that the conduits are watertight to prevent moisture ingress. Use appropriate sealing compounds and fittings to seal all joints and terminations. In areas with high water tables, consider using submersible cables that are designed to withstand prolonged immersion in water. Temperature variations can also affect the performance of high-voltage cables. Extreme heat can accelerate insulation degradation, while extreme cold can make the insulation brittle and prone to cracking. Choose cables with insulation materials that are rated for the expected temperature range. In areas with wide temperature swings, consider using cables with expansion joints to accommodate thermal expansion and contraction. Chemical exposure can also be a concern, especially in industrial environments. Certain chemicals can react with the cable insulation, causing it to swell, crack, or dissolve. Identify any potential chemical hazards in the area and choose cables with insulation materials that are resistant to those chemicals. Mechanical protection is another important consideration. High-voltage cables can be damaged by physical stress, abrasion, or impact. Conduits provide a degree of mechanical protection, but it's also important to protect the cables from damage during installation and maintenance. Use cable rollers and pulling lubricants to minimize friction during cable pulling. Avoid sharp bends or kinks in the cables, as these can create stress points that can lead to failure. When installing cables in areas where they may be exposed to physical damage, consider using armored cables or additional protective measures, such as concrete encasement. Advanced monitoring techniques can be used to detect potential problems before they lead to catastrophic failures. Partial discharge monitoring is a technique that detects the presence of small electrical discharges within the cable insulation. These discharges are often a sign of insulation degradation and can indicate a potential failure. Fiber optic sensing can be used to monitor the temperature and strain of high-voltage cables. Fiber optic sensors are embedded within the cable insulation and can provide real-time data on cable conditions. This data can be used to detect hotspots, overloads, or other anomalies that could lead to failure. Infrared thermography can be used to detect hotspots on cable terminations and splices. Hotspots are often a sign of loose connections, corrosion, or other problems that can lead to failure. By regularly monitoring high-voltage cable installations using these advanced techniques, potential problems can be detected early and corrected before they lead to costly and dangerous failures. In addition to the above, consider the impact of electromagnetic interference (EMI) on nearby equipment. High-voltage cables can generate significant electromagnetic fields that can interfere with the operation of sensitive electronic devices. To minimize EMI, use shielded cables and install them in grounded metal conduits. Also, keep high-voltage cables away from sensitive electronic equipment. Finally, remember that high-voltage cable installations are subject to strict regulations and codes. Consult with a qualified electrical engineer or inspector to ensure that your installation complies with all applicable requirements. By taking all of these factors into account, you can ensure the safe, reliable, and long-lasting operation of your high-voltage cable installations. The principles of electrical safety are paramount when dealing with high-voltage systems. Always adhere to lockout-tagout procedures before commencing any work on electrical equipment. This involves energizing the circuit, locking the disconnecting means, and tagging it to indicate that work is in progress. Verify that the circuit is de-energized using a calibrated voltage tester before touching any conductors. Wear appropriate personal protective equipment, including insulated gloves, safety glasses, and flame-resistant clothing. Maintain a safe working distance from energized equipment. The safe working distance depends on the voltage of the equipment and is specified in relevant safety standards. Never work alone on high voltage systems. Always have a qualified coworker present to assist in case of an emergency. Be aware of your surroundings and identify any potential hazards, such as overhead power lines, underground utilities, or flammable materials. Use insulated tools and equipment when working on or near energized equipment. Inspect tools and equipment before use to ensure that they are in good condition and free from defects. Follow proper grounding procedures to minimize the risk of electric shock. Ensure that all metal enclosures and equipment are properly grounded. Never bypass or disable safety devices such as ground fault circuit interrupters. GSCIs. Report any unsafe conditions or practices to your supervisor immediately. Participate in regular safety training to stay up to date on the latest safety procedures and best practices. By following these electrical safety principles, you can minimize the risk of accidents and injuries when working with high voltage systems. Furthermore, continuous education and training are essential for staying abreast of advancements in cable technology and installation practices. Attend industry conferences, workshops, and seminars to learn about new products, techniques, and regulations. Subscribe to relevant industry publications and online resources to stay informed about the latest developments in the field. Seek certifications from recognized organizations to demonstrate your knowledge and skills. By investing in your professional development, you can enhance your competence and contribute to the safety and reliability of high-voltage cable installations. Remember that high-voltage cable installations are complex systems that require careful planning, design, installation, and maintenance. By following best practices and adhering to safety guidelines, you can ensure the safe, reliable, and long-lasting operation of these critical electrical systems. Consider the use of cable management systems to support and organize cables within the conduit. Cable trays, cable ladders, and other cable management systems can help to prevent cable sagging, tangling, and abrasion. Also, consider the use of cable markers to identify cables and circuits. Cable markers can help to prevent errors during maintenance and troubleshooting. When selecting cable markers, choose materials that are durable, weather-resistant, and easy to read. Finally, document all aspects of the high-voltage cable installation, including cable specifications, conduit layout, grounding details, and test results. This documentation will be invaluable for future maintenance and troubleshooting. Store the documentation in a safe and accessible location. In conclusion, meticulous planning, adherence to safety protocols, continuous learning, and comprehensive documentation are the cornerstones of successful high-voltage cable installations.